Welcome back. Last part. Let's get into the last part of this, okay? So remember, we're still doing friction. Now, we need to look at the graph. Graphing is very important in science. It helps us explain relationships. So if I took the animation we did earlier and we could plot a graph of what we saw, this is what it would look like. So we get a graph that looks like this. We have a graph of frictional force on a horizontally applied force, so like the man pushing the box, for an object that starts to move on a rough surface. So there's friction, okay? This is what happens. Friction force is my dependent variable. It was what we were measuring. Applied force was the independent. It's what we changed. So this first part, this purple line that you can see that goes up at an angle, that is what happens with static. Remember, the static frictional force got bigger and bigger and bigger and bigger, okay? So over here, we have our static friction, which is equal to the applied force, but can be smaller than the maximum friction, or can be equal to the maximum friction. Okay, that's what this little part says here. Remember, this equation is for working out maximum static friction. So here, this whole section here, the object's at rest. It's not moving. Then we get to this point, and there's an immediate drop. You saw that. There's no time frame. It's immediate. It drops. That's maximum. Now we get kinetic friction, which is a constant. So at that point, it starts moving. And this is always difficult because when we describe it in questions, I often get asked, but ma'am, it's already moving. Why is it static friction? When the question describes it as the force applied as it starts to move, they're referring to the maximum static friction. It feels weird because there's movement involved. The key word is starts to move. That's the key part there, okay? This line here, that horizontal line, that's the kinetic friction. That is constant. That will not change. Doesn't matter what I do with the applied force. If it's moving, and you saw that in the animation, if I take the applied force away, that friction will stop it from moving. It'll eventually stop. Once it stops, no friction. Friction's gone to static, no applied force, it's zero. Okay? This is an important graph. Very, very, very important graph for you to know. Okay? Now, let's do a question, because that always makes it make a bit more sense. A toy box and its contents with a mass of 20 kilograms. This is a very big toy box. Okay, let's just go. It's 20 kilograms. Stands on a horizontal floor, so it's flat. The coefficient of static friction between the floor and the toolbox is 0.4. So first of all, keywords, stands. In other words, it's not moving, static friction. Coefficient of static friction, 0.4. They are giving me mu s. When you read a question, underline important things. See what the important words are. That helps you put it into context, okay? Then they say, calculate the maximum horizontal force that a child must exert to just start the toy box moving. Just start moving, maximum static friction, okay? So they're saying to you, what is, that should be an S, not a, okay? So they're going, I need to know maximum static friction, because as it just starts to move, my applied force is equal to my maximum static friction. We know that that's going to be mu s Fn. Hopefully you're now going, but we don't know Fn. Of course we do. Remember, toy box, okay, gravity acts down, What resists gravity? The normal force. Because that's vertically like this and it's moving horizontally, the normal force is equal to the gravitational force. And we know that we can calculate gravity by going mg. So let's think about this. I know mu s, they told me it was 0.4. Okay? I know Fn because it's going to be equal to Fg. So I'm actually going to put that in straight away. My mass was 20, and we remember because we've done this lots, G is 9.8. Okay? Now we use our calculators. Okay, so we take our calculators out. Let's just put it so we can see. Let's put it on the side. So here, we've got 0.4 times by 20 times by 9.8. No fractions, okay? So we're going to change it into a decimal, 78.94. Oh, wait. Let me just 78.4. I don't know where I got the 9 from. Let's just go with it. Now, what we've calculated is static friction. The question wanted minimum horizontal force. So that's the applied force. So now we have to answer the question. That means that the applied force from the boy, F applied, is going to be 78.4 newtons. In the past, I've told you vectors are forces are a vector. I cannot put a direction in terms of left, right, up, down. I didn't tell you which way the boy or the child was pushing the toy box. What I can tell you though is this needs to go in the forward direction. That's as good as it can get for direction here. Because I don't have a diagram, if I had a diagram, I could relate it to a diagram. If they had said pushing it west or south or east or whatever, then I could do that, but they didn't. Forward's fine. Forward's a direction. Okay? We all good? All right. Now, a model car and some blocks together have a mass of 2.5 kilograms are taken out of the toy box by the child. He's having some playtime. That's good. Calculate the new force needed to move the toy box. That should say toy box, not toolbox. Now, when we look at this, first of all, we've taken stuff out of the toy box. Mass is smaller. That means a smaller force. But the first thing we need to know is what is the new mass? So my original mass was 20 kilograms. We've now taken out 2.5. So that gives me 17.5 kilograms. That is the only thing that has changed in this question. What they're wanting you to see is that the applied force is actually going to be smaller. So we're still going to do maximum friction mu s didn't change. It's still the toy box on the same surface. So it's still 0.4. But now my mass isn't 20, it's 17.5. G is still 9.8. Okay? We take our calculators out because we can't do this in our head, so we're going to get rid of what's there. 0.4 times 17.5 times 9.8. Oh, no. There we go. 68.6. It's smaller. So, 68.6 newtons. We expected it to be smaller because the mass was smaller. Mass being smaller made the normal force smaller, and they're directly proportional. We need to answer the question. .6 newtons forward. Smaller mass, smaller friction. All right, so, gave myself lots of space. Here's our summary of what we've done, okay? Friction opposes motion. Please, that's the important thing. It opposes motion, not applied force. Static friction is the tendency to move. This word's quite important because friction opposes motion, which I've just said to you, but with a static object, it's not moving yet. So it's opposing the way it wants to move, okay? Static, stationary object. Kinetic friction opposes motion of a moving object. Moving. Kinetic, moving. Like kinetic energy. It's got to be moving, okay? Kinetic friction, always smaller than maximum static. Always, always, always. Friction, this is the big one out of all the properties we did, is dependent on the normal force. That's the big thing. That determines friction for us. We can't change the amount of friction between the coefficient because of the type of surfaces, but we absolutely can affect the normal force. The coefficient of friction, now this is a definition. This is the weird one when it comes to your exams because they may say to you, what is the coefficient of friction general? Or they might say kinetic friction or static friction. You've just then got to add in static or kinetic in the definition. So the coefficient of friction, which is the symbol mu, and we either put an S or a K, is the ratio of the friction and the normal force. Ratio means division. Coefficient, no units. Okay, very important. There's mu S with maximum static friction, mu K, kinetic friction in the normal. Okay? Just as an aside, you may see these equations with an N instead of Fn. Okay? They're given to you on your information sheet. That's always nice. We like it when they give us equations. And that brings us to the end of today. So we've finished friction. We've still got to look at force and motion, and we're still going to look at Newton's second law, but that's coming up in lessons to come. But we're done for today.